So let's see what this feels like, going back to the early chapters and reviewing some of these problems. So I'm going to start with this first problem, and we've got 8 problems. They're a little bit shorter, so I think we'll be fine. I think we'll fit all of this in. So it says that we have an object 30 centimeters in front of a concave mirror. Oh my gosh, a concave mirror. When's the last time we spoke those words? That was many, many weeks ago. And that mirror has a radius of 20 centimeters. Draw a ray diagram to estimate the image location and magnification. So here's the diagram. Here is the mirror. Now, if you remember with the ray diagrams, we want to get that central line and the line representing the lens or the mirror perpendicular. Just draw those very prominent. Don't try and include curvature on this, but go ahead and write that down somewhere. So what they're saying is it's concave. So if the mirror is concave, that's considered a positive radius of curvature, and it will have a positive focal length, and it's considered to be a converging mirror. That's good news, I think. Converging sounds easier than diverging, if I remember back in those chapters. So I drew this in, and did I scale it? Okay, I just want the magnification. So I've got HO here. I drew the line straight in, and then I brought it back through the focal point. So the focal length is 1/2 the radius. That puts the focal length at 10 centimeters. And then, what was D? Oh, DO is 30. So I have a ruler. I did this very carefully. You guys need to be able to do the same. So 10 centimeters, 20 centimeters, 30. I carefully measured those out. And that parallel line comes back through the focal point. And then there's a line through the focal point on the way in, and then back out parallel. I guess I didn't even bother with that third line. I should have. The third line would have come right into the center of the plane of the mirror, or the curved portion of the mirror, and then come back out at the same angle. That's not as reliable anyway. So taking the 2 lines through the focal points, that's good. If I'd followed up with the third line, it would just be to kind of a reality check to make sure I hadn't done something crazy. So it looks good. Anyway, it looks fine with those 2 lines there. Now, I also did a mathematical check. So I had the numbers. Go ahead and plug them in. And so I put the numbers in. DI is 15, and that's what it looks like in my diagram. That's where the 2 lines crossed the intersection, and then I drew my image. Now, the magnification then, calculating the magnification from the distances, suggests a magnification that is inverted, an image that's inverted, and a magnification of 1/2, and that looks completely plausible from the diagram. Okay, so that's what you're shooting for, is enough precision that you can do a meaningful comparison with the numbers that you come up with. All right, so that's, lenses and mirrors, specifically mirrors. And then here we have 3 light sources. So this is kind of a 3-slit problem. Now, coherent just means that when the light comes in, so when the light's approaching these 3 slits, it's a plane wave coming in, and that means that if I take a snapshot, all 3 of these are right in phase with each other. And if you think back, all the formulas we derived for interference effects, that's what we always assumed, is that we would have everything in phase where it reached the 3 slits. And so what is it they want us to solve for? It says that the wavelength of the light's 500 nanometers. The D's, the D here and the D here, is 1,000 nanometers. But what's different this time is I've got double the amplitude on that middle slit. So the middle slit's a little wider, and the amplitude's larger. And I think almost every example we've looked at, probably all of them, the amplitudes were always the same. Oh no, we've got to figure out how to take into account an amplitude that's bigger. So here's kind of a diagram of what's going on. And I like these circular screens, especially on a problem where things are a little unfamiliar. it gives me a little more security that I'll be able to get through the problem for whatever reason. Now the phasor diagram for this, I would have 3 paths, and the paths would consist of one path has amplitude A, and then there's going to be a phase shift, and that phase shift can be written on the exterior angle here. And then here is the middle path, which has an amplitude of 2A, and then I have another phase shift, another exterior angle here of A, and then to get A total I can connect the ends of those phasors, and I can do a little trig, not really, mostly just adding things together, a little trig. So I have a 2A in the middle, I have an A cosine phi and an A cosine phi, so I got 2 of those. So A total works out to be 2A 1 plus cosine phi. Given what the problem's asking for, I don't feel like I'm obligated to do any trig identities and try and, it already seems reasonably simplified. There are those half-angle formulas that you could try. I didn't do it, I guess we could have. In any case, the angle here is going to be, the phase angles are going to be expressible in terms of m times 2 pi. That's our conversion factor between working in radians, the phis are in radians, and the m values are in cycles. I hope this seems vaguely familiar. So the peak values, I mean, I can look at this. Did it ask for intensity? It never did. Or did it? And I left that out. Am I going to lose points? Huh. Well, it does have intensity in there, but it just wants to find out where the peaks will be. And I never squared it to get intensity. I'm going to imagine squaring it, just, you know. So the intensity here would come from squaring the A total. That's going to give me 4A squared, something like I naught out front. The key feature here is it's going to be 1 plus cosine phi. Now, I want to find out what the peaks, where the peaks are going to show up. The peaks, I can already look at the formula. I don't have to take any derivatives. The peaks are going to be when cosine phi is 1. That's it, done, right? That's going to give me the largest possible values. The zeros are going to occur. There are zeros, and they occur when cosine of phi is negative 1. So the values at which cosine of phi is 1 is going to be phi of 0, 2 pi, 4 pi. Those are the m values, 0, 1, 2. So surprisingly enough, we're back to having all the peaks show up at integer values of m. That's kind of interesting, I guess. Okay. And then using d sine theta equals m lambda, what we can do is, and then what I did here with this 1/2, the lambda was 500, the d value was 1,000 nanometers, that's just a half. And then I just plugged values in for different m values, and then solved for the angles. So I was able to show that the peaks would occur at angles of 0, 30, and 90. We found all the peaks because we went all the way to 90. Did it ask us to find them all? It kind of did. So we got them all. We only have to go out to 90. And then the zeros are going to be at the half integer values because that's when cosine phi is negative 1. So surprisingly, 3 slits where the middle one is 2 amplitudes gives us kind of a very similar pattern to 2-slit interference. Kind of interesting. Okay, at least as far as where the locations of the peaks and zeros are. All right. So mirrors and lenses, interference. Let's move on to relativity. We've got this spaceship. It's 40,000 kilogram spaceship. There's a planet 10 light years away. It only takes 5 years in the reference system of the spacecraft. The spacecraft is using a radio transmitter with a wavelength of 8 centimeters. What will be the wavelength, frequency, and energy of the photons back on Earth? And so here are the 2 reference systems. We did a problem similar to this. Did we have this on one of the midterms? So here is the Earth planet, and they're 10 light years away. But from the spacecraft reference, the Earth and the planet are moving, and the distance between them will be shortened. That's going to be a length contraction effect. And I wrote down the wavelength here just as a reminder. We're not there yet to make use of it. We got to find out how fast we're moving. Now, this is one of those situations where they gave us a distance in one reference frame, but they gave us a time in a different reference frame. So we have to piece the formulas together. So I said that the V would come from calculating L naught over T naught, but I don't know T naught, right? But I do know that T naught is equal to gamma times T, which I do know. So I substituted in gamma times T, and then this needs a factor of gamma on it. So there needs to be a gamma right there. This is 10 light years over 5 years, and that leaves us with 2 times C, but there needs to be a factor of gamma underneath. Now, I dropped my gamma, but I picked it back up right here. So here, I've written it as gamma times V is 2 times C, which is equal to, or gamma times V, rather. If I take gamma times V, that is going to give me gamma squared minus 1 square root times C. So it's really these two that match up, and then they're equal to the one in the middle. When I go through and solve for gamma, I get gamma squared is 1 plus 2 squared equals 5. I get gamma is the square root of 5. I need to travel at a gamma of 2.236. Now here is the formula for V in terms of gamma. And I am using that again. I used it once here to get to this formula. Now I'm plugging it back in. I'm getting 0.8944 C. So that's how fast we need to travel. Now the redshift that we have, because the spacecraft is moving away from Earth, and so sending light back towards Earth, the light will be redshifted when it's observed on Earth. And so I'm using a redshift formula that we've developed, and it worked out to be 33.9 centimeters. I did not bother to get the frequency. Oh no. The frequency and the energy are not there. So you guys can get the frequency and energy, right? Sorry about that. I did not do that. Okay, problem 4. We've got a proton within a nucleus. There's a region of 10 femtometers that it's confined within. So let's bring out the infinite potential well model. Here it's being called the particle in a box. That's the infinite potential well. To estimate the energy and wavelength of photons generated if the proton drops from energy state 2 to energy state 1. Now, we remember that protons, we did something similar in class or in lecture, and what we found is the proton is confined to such a small region, the kinetic energies are really high in these states. So working from the formula for an infinite potential well, we ended up with, plugging in the numbers here, this was what, 10 femtometers? We ended up with 2.05 MeV for this first state and 8.19. It says that the photons generated are going to be 6.14 MeV. That's enormous. These are gamma rays, right? So when the nuclear protons and neutrons in the nucleus drop from excited states into lower quantum states, lower energy states, the photons generated are in the gamma part of the spectrum. Those are really high energy photons. And then the wavelength here is 202 femtometers. So that's pretty remarkable. Okay, I want to make sure we get to those last two because we do have midterm 4 coming up, but then it's, we want to look at all of these. So moving on to problem 5 is looking at X-rays produced in transitions of electrons, not protons anymore. Now we're looking at electrons from state 2 to state 1 in metals, and they don't tell us which metal we're looking at. They do tell us that in this metal, the X-ray photons being produced have a wavelength of 72 picometers. So here is the 72 picometers. Here is the energy formula for state 1. Here is the energy formula for state 2. And then the key feature here is to keep track of the Z effectives. And so the energy of the photons being produced, hc over lambda, is 17,200 eV. That's a lot of eV. The energy of a photon based on these formulas should be E2 minus E1. That would be 13.6 eV times Z effective squared, 1 over 1 squared minus 1 over 2 squared. And what that gives us is a formula that looks a little funny. What happened to it? So there's a... Oh, it's fine. That's a Z, right? Handwriting's off a bit. That's what my Z's look like. I cross them in the middle, which you guys know, I hope by now, because I don't want them to get confused with 2's. But that one's a little sloppy. So there's the Z squared effective. So using that formula, the Z squared effective is 17,200 divided by 10.2 eV. The EVs drop out. I took a square root. Z effective then is 41. That means Z is 42. Looking this on a periodic table, it's molybdenum. All right? And yes, you will be asked to pronounce molybdenum on the final exam, so be prepared for that. All right, let's see. That was problem 5. Problem 6 is looking at hydrogen chloride molecules. Hey, those are diatomic, and we're looking at vibrational energy spacings, and it's observed to be 0.359 eV. So from this, find the bond stiffness, and along the way, calculate the amplitudes of vibrations for the two states. So let's see what we've got here. This is my HCl diatomic molecule. The ground state should have an energy of 1/2 h bar omega. The first excited state will be 3/2 h bar omega. And so h bar omega is equal to the difference between the two energies, and that's 0.359 eV. I converted that over into joules because we're going to be looking at bond stiffness. And when we've looked at bond stiffness before, if you remember, those typically get written in standard units of newtons per meter. Even though we're at the scale of these little tiny chemical bonds inside molecules, those stiffnesses have kind of macroscopic values that go along with them. That's kind of interesting that they're so stiff. All right, so for this, what we did was we went in and calculated what omega is. Now remember, omega is just for convenience. We don't really think of vibration as these nuclei following trajectories. It's a probability distribution. So I'm going to take the omega, which we've calculated now based on the energy separation, and say, hey, omega really should be thought of as k over mu square root, where k is the bond stiffness. That's what we want, is that k value. So k is equal to mu times omega squared. We can get the reduced mass because, did they tell us the mass of the, yeah. So they said specifically, this molecule that we're looking at is the 1 isotope of hydrogen, and it's the 35 isotope of chlorine. So we got to know which masses to use, and that means we have to know the isotope for each of these. Now, using the formulas for the reduced mass, that works out to be 0.972 atomic mass units, and then conversion into kilograms. Make sure you know how to convert that. So my favorite conversion there is 1 gram is equal to Avogadro's number of Avogadro's number of atomic mass units. Anyway, use the conversion in the book, cover whichever one's there. Make sure you know how to convert back and forth for that. So we've got the mu, we've got the omegas. Plug those together, and everything in standard units now, as if it were a macroscopic object. and we're ending up with 478 newtons per meter. So that's a pretty good stiffness for this little tiny hydrogen chloride molecule. Okay, so it's not hydrochloric acid, it's not in solution, it's just a vapor form, I guess, of a hydrogen chloride molecule that we're considering here. Now, to calculate amplitudes, what we said we could do is take the energy 1/2 h bar omega and set that equal to 1/2 k amplitude squared. Now, we can apply that for each of the states. So for the ground state, there's going to be an amplitude. When we go to the excited state, there will be a larger amplitude, but the k value stays the same, right? So the k is not changing. We know what the k is, and using these formulas, we end up with 11 picometers of vibration, 11 picometers, you know, roughly 11 picometers of variation in the bond length in the ground state. But in the excited state, that jumps to 19 picometers. Did it ever say what the bond length is? It never says. So the bond length in a molecule like that, it's probably, you know, between 100 and maybe more like 150. Chlorine's a pretty good sized atom. Maybe 100 and 150, I'm going to guess 140 picometers. And then we're seeing this much vibration in that. Okay. All right. So, let's get down to those last two. The last two problems that we have here are going to be relevant not just for the final, but for the upcoming midterm, which is coming really soon. Did I mention that? So on problem 7 is saying, let's imagine a nuclear power plant. Again, it's one of our 1,000 megawatt power plants. On this one, we have an efficiency. Notice, I think we've looked at examples before. Sometimes we use efficiency, sometimes we don't. This one has it there, and so you should understand how to put an efficiency into your calculations. I'm going to say, if I put efficiency into a problem like this, at least half the class gets it backwards. They use the inverse. And so what you have to tell yourself is, because of the limited efficiency of the power plant, the thermal efficiency, you're going to need more fuel, not less. Anyway, let's see how this is set up. So it says that we're going to operate the power plant for a year. There is my 31.6 million seconds each year. And here we are, there's my 1,000 megawatt power plant. And here is my efficiency. So what we're generating in the power plant is electricity. So if they say the power plant is 1,000 megawatts, that's 1,000 megawatts of electrical power. So that's what we have here, this 10 to the 9 joules. 10 to the 9 joules is the electric energy. And for every 40 joules of electricity, I had to put in 1,000 joules of thermal energy, and the electrical energies cancel. All right, so that's the way, you know, for me, I just do this dimensional analysis and make sure that the electrical energy and the electrical energy cancel. And that guarantees that I've got the, well, it mostly guarantees that I have the ratio in the correct order and not its inverse. Notice the way it's written, that factor is greater than 1, and because we have a limited thermal efficiency, we're going to need more energy to operate our plant. Now here, we went from joules back into MeV, and I went back and used the textbook's traditional value of 200 MeV. Is that what it's? Yeah, it says that in the problem. So again, that's the number I always see in textbooks. I guess I have to start looking at more fission reactions and see how much variation there is. It seems like whenever I see one, it always comes in lower, you know, more like 170 or 180 rather than 200. But so this is the number of uranium-235s. I need one of those for each of these reactions. And what this calculation turned out to be is, for operating for 1 year, I need 2.47 10 to the 27 uranium-235s. And then I did a conversion with the molar mass of uranium-235, which is 235 grams per mole, and it says I need about a ton. I need a ton of uranium-235 to operate this very nicely sized power plant that's going to provide electrical energy for a pretty good sized community. And all it's going to take is a ton of uranium-235, and then at the end of the year, I will have tons and tons of radioactive material, which I'll have to somehow find a place to store, because it's going to be radioactive for thousands of years. That's the downside. So it is a lot of energy. There's no carbon dioxide that we produced here, but we do have all the radioactive waste material from the fission reactions, and all the neutrons that were generated. Okay, that's a good problem for the midterm and the final. Ooh, we're down to the last practice problem for today's review, and that last and then it's just down to the midterm and the final, right? And I do have office hours ongoing. Take a look and see what office hours are available. Make sure that you plan far enough in advance that make sure you just start working in advance with all of the review. So that you're well prepared for the midterm and well prepared for the final. Set up a schedule, set up many days in advance, and start planning to work your way through all of these examples. And it shouldn't be for the first time, it should be a review as you go through. So this last problem is saying the intensity of the sunlight reaching the location where the Earth is about 1,400 watts per square meter. The mass of the sun is 2 times 10 to the 30th kilograms. The distance between the center of the sun to the center of the Earth is 150 million kilometers. If the sun were entirely starting out as 100% hydrogen and produced its energy through fusion reactions from hydrogen to helium, what would the lifetime of the sun be at its current power output? How long is the sun going to last? That seems like a pretty relevant problem. So let's do that. So here's the sun. It's generating all this light. The light's spreading out. Here is Earth's location. I'm measuring from center of the sun out to center of Earth. And the luminosity of the sun is going to be related to the intensity of light on Earth. Notice they gave us the intensity. The intensity here is the 1,400 watts per square meter. If I multiply that by the surface area of that sphere, I'm going to get the luminosity of the sun, which is the total power output of the sun. So the distance was 150 times 10 to the 9th meters. The intensity was 1,400 watts per square meter. Using this formula, I'm finding that currently the sun is generating energy. The light energy that it's generating is very close to 4 times 10 to the 26th watts. That is a lot of watts. Now the idea of this is if the sun keeps shining with that luminosity, how long until it runs out of fuel? So the fuel then is hydrogen 1, and you guys should know well from class, we looked at this fusion reaction in a lot of detail. It takes 4 hydrogen 1s, 4 protons, to generate a helium-4 nucleus. Along the way, 2 of those protons have to turn into neutrons. When the protons turn into neutrons, we generate neutrinos as well as anti-electrons, and that some of the energy in this reaction is kind of hidden. There's a series of steps. Includes anti-electrons and electrons reacting, matter and antimatter reactions, reacting to generate somewhere between 5 and 10% of the energy of a star. And so the Q value for this reaction, 26.7 MeV. And we had taken this approach, I'm going to use it here. We said one way to solve the problems is to calculate a fraction of the mass that is going to be converted into energy. And for this particular fusion reaction, we're getting almost 1%. We're getting 1 part, well, 0.7, 0.8, something like that, percent. One part in 140 is going to disappear. The mass is going to be gone, and it's going to be replaced with energy, with kinetic energy. So if we take the energy we're going to generate then is that fraction, 1 part in 140, of the total mc squared of the sun. So we're taking the whole mc squared. Now, we have to make sure we get that fraction in there. It's not that the whole sun is going to disappear and become energy, but it is, you know, getting close to 1% of the mass will be gone. Anyway, it says that if we have this much hydrogen, we could generate, using this reaction, 1.29 10 to the 45 joules. Now, at the end of the day, we won't have any hydrogen left, assuming this. All we'll have left is a sphere of helium-4. We can open up a balloon factory or something. The neutrinos are going to fly off, so it's going to flood the surrounding space with, which is already happening, with neutrinos. It's going to happen over billions of years, I guess. Calculating, they gave us the masses, right? There they are. Hydrogen 1 and helium. We're going to treat the neutrinos as massless. And that says that the Q value then is 26.7. That's how we got this. Okay, so I guess we're down to time. So I guess I kind of skipped that part earlier, but now came back, and that's how we got the Q value. The total energy available divided by the luminosity, the rate at which the energy is being used. So if I take this much energy, assuming all the hydrogen fuel, and divide it through by this rate of energy usage, I end up with 103 billion years. Now, you guys probably all know the sun is not expected to shine for 100 billion years. It's expected to shine for maybe 10. And we think we're halfway through that. So where have we been a little too optimistic? And one thing we can point to, let's point to a few things here. The sun did not start out 100% hydrogen. It turns out that during that early plasma phase in the universe, about 25% of the protons fused into helium-4. So all the stars, when they formed, already have 25% composition of helium. So we don't have 100% hydrogen. Only about 75% of this, or 1.5, is that right? 1.5, and that's going to take us from 100 billion years down to 75 billion years. That still sounds like a good long time. And then, as you probably have guessed, not all the hydrogen is going to fuse. Fusion is not taking place throughout the entire star. Fusion is only taking place in the core, and that means that how much of the hydrogen actually gets used depends on how well mixed the hydrogen is. Is there enough convection going on within the sun that the hydrogen, eventually all the hydrogen will get pulled through the core, and we don't think it will. So we think that when the core runs out of fuel, most of the sun will still be hydrogen. It's just, it's never gone near the core, and so it's never gone through a fusion process. So anyway, that's where the 10 billion years estimate comes from. We didn't start out with 100% hydrogen, and of the hydrogen we did start with, most of it will never fuse because it's not going to find its way to the core. Okay, it's going to stay in the outer layers. All right, it's a good problem to end on, right? So calculating kind of how much fuel. If you went back 100 years, maybe a little more, 110 years, and asked the best physicists in the world, how does the sun shine? How does it generate all that energy for the enormous amount of time that the solar system has been around? And no one would have known. Nuclear energies were just not understood at that time. In fact, the nucleus wasn't established until, what, 1913 or something like that. So anyway, it's fairly recent that we actually understand, and now we can sit down see just how much energy is generated in nuclear reactions, and realize that, yeah, that's enough energy to have a star shine for a good long time. So, all right, I think that wraps it up for today. So, again, if you guys have questions, stop by. Let's get those questions looked at. Start, if you haven't started the review process already, I assume you have because you're watching this, get started right away. Set a schedule for preparing for this fourth midterm and final. All right?